Hello everyone, this is Professor Keehn. Last week and this week you've been working on this telescope laboratory. Last week you set up the Keplerian telescope and you also did the exercises on the thin lens equation. What I'd like to do right now is just give you a few pointers on finishing this lab. You have 4 more sections: the magnification section, the spherical aberration section, the angular width section, and the refracting telescope theory section. So let me just make a couple of comments on that. First of all, let's look at the section on magnification. So for the magnification section, let me label this right here. The section on magnification, what you're doing is you're going to be looking at the data that you collected for your thin lens equation data, where you had the lens and then you had your light box with the arrow pointing like this. So this was your light box, this was your lens, and this was your screen over here. And then you measured the object distance and you measured the image distance. You also should have measured the height of your object and the height of the image that was projected on here. So this is the height of the image, okay, from whatever. It's an inverted image, so it looked like that. So it was, the relationship between the height of the object and the height of the image, by the way, is called the magnification. It's the height of the image divided by the height of the object. So if the image is bigger than the object, you have a magnification greater than 1, and if you have the image less than the object, you have a magnification of less than 1. And by the way, if it's inverted, it will be negative. So this will be a negative number if it's inverted. And that's just the convention we use for meaning an inverted image, it's negative. So in this section on magnification, you're going to be going through looking at all of your data and calculating the magnification for each of your data points. That's a pretty straightforward thing. You don't really need to collect any more data for that. What about the section on spherical aberration? Oops. The section on spherical aberration. Well, let me just say something about what spherical aberration is, first of all. So if you have a lens, we talked about how if you have an object, that's kind of not a very straight line. Let me try that again. This is the axis right there. If you have some object right here, let's say it's a glowing object like what you're using in this light box in the lab. You have light rays that are coming off of this object in all different directions, right? And some of these are going through the lens and some of them are missing the lens. Let's just consider the ones that are going through the lens. So they're going like this. They're going to be bending at both of the interfaces here, and they're going to be forming some image. Oops, this is not a very, well, this is a terrible drawing. Somehow my drawing skills are really bad this morning. Let me go to precision mode. Whoop. So if you think about a ray of light like this, and then it's bending like this, and another ray of light here that is going through the center of the lens, and then another ray of light, let's say like here, it's going more through the bottom of the lens. What's going to happen is you are going to get an image of the object over here. It's an inverted image. And the idea is that all of those light rays are converging at in a particular plane. So if we're looking at these orange light rays that I've drawn coming from the tip, they all converge down here at the tip of this. We could have taken light rays from the bottom of this arrow also, looked at 3 of those, and we would have seen that they all converge right here. So the image, this right here, is called the image plane. It occurs at a distance di, the image distance from the lens. Now, that's a bit of an oversimplification, because if we were a little bit more careful, we would notice that some of these rays, in particular, the rays that are coming through the very top of the lens up here, they actually don't converge right at the same location. They converge maybe a little bit beyond. And furthermore, the rays that are going to the very bottom of the lens, way down here, likewise don't converge at quite the right location. They converge back here. And generally speaking, the rays that go through the edges of a lens tend to not converge in the same plane as the rays that are going through the middle region of the lens. And that is what we mean by spherical aberration. That is, when you have rays going through the edges of a lens, they don't quite focus in the right plane and it creates some blurring. How can you prevent this? Well, one way to prevent this is by using an aperture or an iris like this that will block any rays that are supposed to go through the edges, or that would have gone through the edges of the lens. If you block those, then the only ones that get through are the ones that come through the middle, and they focus in the correct plane, and you'll get a sharper image. So by using an aperture, the image can be sharpened, made clearer. And the smaller the aperture, the more sharp the image you get. And there's a trade-off here in that as you make the aperture smaller and smaller, less and less light gets through the lens, and so the image also gets dimmer. So although it's a sharper image, it's a dimmer image as well. You can actually do this. If any of you wear glasses, take your glasses off and take your glasses off and look at some distant object, and it will be blurry, of course, because you don't have your glasses on. But then hold your fingers in a little circle like this and look through the little hole in your fingers. And what you'll notice if you look at a distant object through a tiny hole, it's going to look much sharper, much clearer, almost like you were wearing your glasses. Why is this? Because you're creating an aperture, and the light that's going into the lens of your eye, you're getting rid of the light that's going through the parts of your lens that are on the edges that tend to be the ones that produce a blurry image. So go ahead and try this. It's really fascinating. You basically see a much dimmer image, of course, but it's going to be sharper because you're getting rid of the spherical aberration of your eye. Any case, what you're going to be doing in this part of the lab is you're going to be using irises or apertures of different sizes. They should be in your bucket of equipment. And you might want to start with just the setup like you did in the previous experiment with the thin lenses, where you set up an object, a single lens, and then make an image. Make the image so it's a pretty decent size, okay? And then look at the sharpness of that image. Kind of, maybe you can use your cell phone, take a picture of the image, see how sharp it looks, and then start putting apertures in front of the lens, right next to the lens, apertures of different sizes. There's like a wheel with apertures of different sizes, and see if the image that you see is sharper. The little lines are more easily resolved. It'll get dimmer, so don't confuse the dimness with the sharpness. It'll definitely get dimmer when you use an aperture, but you should be able to see the image getting sharper as you use apertures. Okay, so that's that part. The next part that you're going to be working on is a section on angular width. I talked about this a bit in lecture this week, so I won't spend much time on this. The idea is that you're going to be looking at your fingernail, okay? And if you hold your finger at some distance from your eye, here's your eye, there's going to be some distance of this object. Also, there's going to be some width of your finger. That's the height of this, h naught. And then you can get the angular width using the formula I gave you before. This will be in radians, height over d naught. That will be the angular width of your fingernail as seen at that distance. And you're going to be holding this right about your near point of your eye. The next thing you're going to be doing is putting a lens, maybe a 5 or 10 centimeter focal length lens in front of your eye, and then you can move your finger in closer, okay, and then that new distance you're holding it at, and there's a new, well, I guess the same height before, you can get a different angle that you see of your fingernail, and hence you can find the angular magnification, which is the ratio of the angle in this case to the angle in this case. Okay, so that's what you're going to be doing there. Now, the last part is refracting telescope theory, and I guess I want to spend the most time talking about this. So let's talk about refracting telescope theory. What I want you to do in this section of the lab is I want you to do an analysis of the telescope that you built back in last week. And in particular, I want to see if you can figure out what the magnification of your telescope is. So you'll need to use your data that you had from the previous time. So what you did, if you remember, is you had your two lenses. I want you to draw, this is an opportunity to draw a ray diagram and try to do precise measurements, okay? So let's suppose you had your object that you were looking at over here, and it has some height. I want you to draw ray diagrams depicting where the image of that object is going to be, okay? This, by the way, was the location of your frosted glass, okay? So that was your image distance from lens 1, which was your objective lens, okay? And here's the object distance from lens 1. And you should have a measurement of that image distance. You may also have a measurement of the height of this little image that appeared on your frosted glass. The point is that you can figure out, using the thin lens equation, what the magnification of this is. You know, if you're using this light box, this was maybe like 2.5 or 3 centimeters. I don't remember how tall that was, but you can figure out the ratio of the height of this compared to the height of the image, and that would be the magnification of lens 1, which would be the ratio of the height of your image 1 divided by the height of your object 1 over here. And then what you can do is you can draw a ray diagram for the rays coming out of this. Now, the important thing to notice is that this image is actually going to lie slightly within your focal length. It'll be just about at, but right near the focal length of lens 2, but just inside of it. And because it's inside of that focal length, what happens is that these rays that are coming from the tip of this image, they will not be converging to your eye. They're going to be slightly diverging right here, okay? And so what does that mean? It means that the image that is formed is these rays right here are going to converge over here, way out here, and so you will perceive an image out here. So this is the height of the image formed by lens 2, okay? And what you can do is by, once again, using the thin lens equation, you can figure out the distance of the image formed by lens 2 if you know the distance of the object that you're looking at with lens 2. Remember, the object for lens 2 is the same as the image from lens 1. And if you know the focal length of lens 2, you can use the thin lens equation to figure out the distance to this one, and then you can also find the magnification, right? So the magnification of lens 2 is going to be the height of image 2 divided by the height of image 1. And remember from lecture, these are also related to these distances right here. So from these distances, you can figure out the magnification of this. And then overall, by comparing the height of your original object to the height of the final image formed, that is going to give you the magnification of your telescope, which would really be the height of the object of lens, I'm sorry, go back for a second. It would be the height of the image formed by lens 2 divided by the height of the object you're looking at with lens 1. So I want you to find the magnification of your entire telescope using this method. So you'll need to go back and look at the measurements when you designed your telescope back in last lab, these various distances that you recorded in your lab book when you designed your telescope. And by the way, this should be about equal to the focal length of the objective lens divided by the focal length of the eyepiece lens. Okay, so hopefully that will get you going on this lab, and I wish you success.